ME347, Example 3, Differential Control Volume Analysis of Fully Developed Lid-Driven Flow Between Parallel Plates. A sealed journal bearing is formed from concentric cylinders. The inner and outer radii are 25 millimeters and 26 millimeters, respectively. The journal length is 100 millimeters, and it turns at 2800 RPM. The gap is filled with oil in laminar motion. The torque needed to turn the journal is 0.2 Newton meters. Solve for the following. A, the velocity distribution as a function of the maximum velocity. B, the mean velocity. C, volumetric flow rate. D, the shear stress distribution. And E, the viscosity of the oil. For part F, discuss if the torque will increase or decrease with time. To solve this problem, we will make several assumptions. First, the bearing is unloaded such that the shaft rotates in the center with symmetric flow. Second, the flow can be modeled as flow between parallel plates because the radius of the bearing is large compared to the height of the gap. Third, we will assume that the fluid is incompressible and that the flow is laminar, fully developed, and steady. Fourth, we will assume negligible end effects for a bearing length that is large compared to the height of the gap. Finally, we will assume there is no pressure drop and there are negligible gravitational effects. For part A, find the velocity distribution as a function of maximum velocity. Since we want to solve for the continuous velocity variation, we need to use the differential form of the governing equations. We begin by defining our coordinate system such that x is in the flow direction, y is across the gap, and y equals 0 is aligned with the outer radius. Thus, the velocity will be 0 at y equals 0 and equal to the angular velocity times the inner radius at y equals h, where h is the outer radius minus the inner radius. Starting with conservation of mass, we find that for the fully developed 2D flow, the oil is behaving like an incompressible liquid, but that is all. Thus, we need to use the momentum equation to solve for how the viscous forces will determine the velocity distribution. Begin by writing the x component of the momentum equation to solve for the x component of velocity. Note that the y and z components will just give us that the velocity is 0 in these directions. For this case, we can neglect gravitational effects and the pressure drop is 0. Expanding the remaining terms, we get the following. Most of these terms are also 0. On the left, for fully developed flow in a constant area passage, both the local and convective accelerations are 0. On the right, again for fully developed flow, the velocity does not change in the x direction. Finally, for 2D flow, the velocity does not change in the z direction. Thus, the equation reduces to a very simple ODE. Integrating twice and applying our two boundary conditions, we can solve for the velocity distribution. Note that the resulting distribution is just a linear function of y. For part B, to find the mean velocity, we integrate the velocity over the area normal to the flow and divide by that area. Note that the average velocity is half of the velocity of the top plate, as expected for a linear velocity distribution. Substituting in, we get an average velocity of 3.67 meters per second. For part C, to find the volumetric flow rate, we multiply the average velocity by the area normal to the flow, which gives a flow rate of 0.367 liters per second. For part D, to find the shear stress distribution, we use the definition of a Newtonian fluid and the stress versus angular strain relationship. For one-dimensional flow, the second term is 0. Substituting in our known velocity profile, we get that the shear stress is constant across the gap. For part E, to find the fluid viscosity, we recall that the torque is equal to the force multiplied by the moment arm. Also, the shear stress is that same force divided by the area of the solid fluid boundary. Combining these definitions to eliminate F and using the shear stress distribution from part D, we solve for the viscosity. Note that the viscosity is proportional to the torque required to spin the bearing, as expected. Substituting in our values, we get a value of 0.0965 Newton seconds per meter squared. Finally, for part F, we want to consider how the torque will change with time. This will depend on how much viscous heating occurs. If it is negligible, the torque will remain about the same. But if it is significant, the viscosity of the oil and the torque will both decrease.